Hello and welcome to Big Picture Walks. It's a nice sunny Saturday morning and we're gonna talk about increasing returns to scale. So as I argued in some episode before, increasing returns to scale is an important phenomenon that is helping growth processes to gain momentum and accelerate over time instead of dying down and slowing down to a stop. What is increasing returns to scale? I think it's convenient to begin with constant returns to scale. So in macroeconomics 101 or in all sorts of basic economic theory, you typically assume that production processes have constant returns to scale. And if you dig into the handbooks to look for explanations of why this is typically assumed, they are typically not too transparent in that. And so the best argument I've found about that is the so-called replication argument. The replication argument is the following. So think about a factory. Okay, you have a factory, it employs a certain amount of capital and a certain number of workers. And then it produces some kind of output. Now imagine you set up a second factory which is just exactly the same as the previous one. So if you take them all together, you employ twice as much capital, twice as many workers, and you produce twice as much output, right? Because you just replicated the same process, so you must get twice as much output. So this is a replication argument. Now, the question is whether we buy it, okay? And it seems that to a certain extent it's correct, but it has its limitations. And these limitations are really apparent if you think about the long run. So I think it's a very nice insight from Paul Romer to divide inputs into rivalrous inputs and non-rivalrous inputs. So the replication argument and the constant returns argument, therefore, works nicely for rivalrous inputs, capital, labor. But if you also add non-rivalrous inputs like ideas, like computer code that can be copied virtually costlessly, this breaks down. So if you think about a factory that uses a certain amount of capital, a certain number of workers, and then a certain number of technological ideas, and then you double everything, including doubling the amount of technological ideas, what you end up with is producing more than twice as much output, because those ideas can be freely used in both factories at the same time. So you see, increasing returns emerge naturally in a framework where some of the inputs are non-rivalrous. Increasing returns are very useful for an economy in the long term because they allow processes of development to create positive feedback loops and feedback on itself and accelerate the process over and over and over without end. Okay. Well, if you formalize this mathematically, you immediately see that it is not always the case, and sometimes even if with increasing returns, you may have growth processes slowing down, but clearly this option is then on the table. So what are the channels through which this mechanism works? Okay, throughout virtually all human history, there was just one channel, and this was technological ideas. So throughout most of the human history, it was the case that new ideas were adopted in production and then used, and since they are non-rivalrous, they created this increasing returns, a feedback loop, and perpetuated itself, and you had lasting growth. However, in the recent days, arguably we also have a second mechanism that strengthens the first one. Now we also have non-rivalrous code that is decoupled from human brains and can be virtually costlessly copied. So that's a second channel through which these increasing returns may work. So what were the technological revolutions that affected software, so ideas, technologies, and also data processing capabilities over the centuries? So we need to start with the cognitive revolution, which happened like 70,000 years ago, and that was the initial moment where humans, the Homo sapiens, have crossed the threshold of cumulative knowledge accumulation and went on to essentially spread across the whole world and eventually rule it. So the first breakthrough in this regard was because the human brain, the human frontal cortex, developed to an extent that it could, on balance, obtain more information, more knowledge than lose, than forget. The main force of the cognitive revolution was increasing the size of a human network that could effectively cooperate. And cooperate not just in hunting and gathering, but also in thinking. If you like, the size of the research network grew thanks to the cognitive revolution, and it reached the size of 150. This is the famous Dunbar's number, after Robin Dunbar, an English psychologist and neuroscientist. The Dunbar's number, 150, is the number of people with whom you can interact and cooperate effectively and keep track of what is happening, in, like, at least briefly, with each of them, and how they are related to others. So manage all these complex social interactions. So the research network, if you like, increased dramatically after the cognitive revolution and enabled us to systematically gain new knowledge. All right, so the second big leap in the size of the research network in the world was the scientific revolution. The scientific revolution was in the 16th century and onwards in Europe, and was marked by the printing press, the universities, the scientific method, mathematization, hypothesis testing, and so on. So one of the big aspects of a scientific revolution was that it increased the effective network size for the global research network. An important effect of the increase in the size of the global research network was that it allowed increasing returns to kick in, and it allowed for an acceleration in growth, either directly or indirectly after causing the Industrial Revolution. Now, on to the digital revolution. That's yet another leap in information processing, in data communication. It's also a huge leap in connectivity. So we have the internet, okay? We have now a global village. Everyone can almost instantly communicate with virtually anyone else in the world. This is another big increase in the size of the research network, which again is very important for increasing the scope of exploiting increasing returns to scale. So what really matters for the pace of growth driven by increasing returns to scale is the size of the global research network, or as you can put it, the immortal collective brain. Because each of us has a brain, but the effects, technological effects across the whole human civilization kick in when we cooperate, when you can merge results of work by many people at the same time. And so what was the scale of operations? What was the size of this immortal collective brain? And arguably, it began with 150. The world was full of disconnected tribes that virtually did not communicate at all, and the ideas didn't spread widely. So basically the size of the connected, cooperating brain was just 150, and was a huge amount of duplication, was a huge amount of loss of information because of this lack of coordination and lack of information communication. But starting from this very low base, the size of the immortal collective brain increased. So slowly but surely, not only the number of people who did some sort of thinking and eventually some sort of scientific research was increasing over time, but also the connectedness of those people was increasing over time. Before the year 1200, there was essentially no communication between Europe, the Middle East on the one hand, and China on the other. Even though there was the same landmass, there was very, very little trade and very little communication between these two areas. And not to mention the Americas, which were completely unknown to everyone in the old world until Christopher Columbus. Okay, let me skip the Viking story because that was in the long run irrelevant. Yeah, so after the scientific revolution, there was another big increase in the number of researchers, in how formal they actually went about doing science. So universities were built, mechanisms were set up for replicability of results, for experimentation, for data constraint theorizing, and so on. And now we have really a bonanza of connectivity. After the digital revolution, we have the internet, we have the World Wide Web, we have efficient search engines, and we go to international conferences where scientists meet their peers from all over the world. So we've come from a world where diffusion of information was so slow that there were at least 7 independent agricultural revolutions in various parts of the globe. Check out Jared Diamond's Guns, Germs and Steel. That's a brilliant book, really exciting to read. So we went from that situation to the modern situation where we have everyone in science writing in the same language, which is English plus the universal language of mathematics. And we have this global web where people can, setting aside censorship in certain countries, freely communicate. And it's not only the researchers, the machines communicate even better. Scalability is buzzword number 1 in the digital era, in the Silicon Valley, for example. So we communicate a lot, machines find communication way easier, they send data way faster and without errors. We communicate slowly, and do we always understand what the others are meaning to tell us? The state of human knowledge these times is incredibly advanced. We have amazing technologies in our disposal, and it's extremely hard to comprehend how they work. What makes us able to push the knowledge frontier ahead? Apparently, there are a few ways how we deal with this. First, we specialize. So there are no Renaissance man anymore. It's impossible because the knowledge is so large and so diverse, it's impossible for people to comprehend more than one narrow area in which they specialize. So that's the first thing. Secondly, we cooperate to an increasing extent. So not only do we go to conferences, but we actually co-author our scientific work to a larger and larger extent, and also we build bigger and bigger consortia to organize, let's say, experiments and some more costly scientific endeavors. Like think about the Large Hadron Collider or the Very Large Telescope in Chile and so on. So this is really a costly enterprise. So you need cooperation. You need big resources. And we also augment our brains in the sense that we are using more and more advanced digital computing techniques. We use computers to do statistics for us, to do simulations. We use internet AI-driven search engines to search relevant information for us. So we help ourselves as much as we can to augment our limited brain capacity. This all means we are very limited in how we process information. So by specializing a lot into narrowly specified field areas, we miss a lot of interdisciplinary insights. We just cannot connect the dots if some of the dots are in one area that someone specializes in, and then another dot is in a faraway area where somebody else specializes in. So communication is difficult not just between the scientists and the general public, where it's clearly difficult, but it's also difficult among scientists themselves, but between disciplines. That's all now. Please like, please share, comment, and subscribe. In particular, I would be very happy if you gave me some feedback on what I'm talking about, on what you would like me to talk about in the future. Maybe you have a different idea on some fundamental questions regarding the human civilization and its future. That would be most appreciated. Thanks. Bye. The Vikings didn't quite know that their Vinland was really America and that it stretched further down. So there was not really this meaningful contact that was established after Christopher Columbus. Contact. Exploitation and colonialism, but okay. Contact. The sign says, "Monument of nature, don't move." Hey, monument of nature, don't move.